Hi, Assalamualaikum. Good morning, good afternoon, good evening, and good night, depending on when and where you're watching this presentation today. My name is Azam Hakim bin Abdullah with number matrix BE250106, and I am from Group 5. And today we will be presenting the multivariable calculus project assignment. These are my group members that we worked alongside to make this slide presentation and all the simulation and calculations.
So my name is Muhammad Khalid bin Osman. My metric card number is DE250061. So I'm going to start with my presentation with what are multiple integrals. Multiple integrals generalize the concept of a definite integral to functions with more than one variable, allowing it for calculations across multi-dimensional spaces. Double integrals measure the volume under a 3D surface, while the triple integral determine properties like mass or charge within a solid object. These mathematical tools are essential for finding the area of complex shapes, locating center of gravity, and analyzing multivariable variable probability. Those things are example for multiple integrals, which is normal multiple integrals, which is double integrals and triple integrals. So for our project here, we got three objectives, which is the first is to work together to solve those questions manually with manual solutions, and second, to verify the answers by using mathematical tools such as MATLAB with software solutions. So the third is to explain the step-by-step solution without relying on pre-written code and demonstrating a deep understanding of the process. There are few methodology that we can get from this group project. The first is identify the problem and define the objectives, variables, and constraints involved in the project. So the second, develop a mathematical model using multi-variable functions to represent the real-world situation. So the third is apply multivariable calculus techniques, multiple integrals, and doing it manually to solve the problem. Next, verify the result to get the graphs or mathematical software using MATLAB or ensure the accuracy of the solution. The last but not the least, analyze and interpret the findings to evaluate their practical application and draw the final conclusion.
Continuing on to the problem statement. Now, Q1, question 1, by changing the following double integrals to polar coordinate, evaluate. We are from group 5, hence we get the question E, and this is our equation. Moving on to question 2, by using double integrals, find the surface area of the portion of, again, since we are group 5, the question is the paraboloid z equals to z squared plus y squared, and below the plane z equals 1. Going to the final question, which is Q3, compute the multiple integrals of set equation, and for both 1 and 2. And then on B, evaluate the following triple integral by using spherical coordinates. This is the calculation. This is the question. On C, the first question is by using polar coordinates, evaluate the equation if R is the region in between circle x power of 2 plus y power of 2 equals to 1 and x power of 2 plus y power of 2 equals to 4 in the first octant. Now on the final one, which is by using double integrals, find the area of the region enclosed by the set equation.
Hello, my name is Kesodaran. My meeting number is CE250120. So for the first question is, we are evaluating this double integral by switching from Cartesian to polar coordinate. As you can see, this is the first problem statement for our manual calculation. Looking at the limits, y goes from 0 to square root 4 minus x squared, and x goes from -2 to 2. This defines the upper semicircle of radius 2 centered at the origin. So next step is the polar conversion. As you can see, we use the standard polar substitution, such as x equals to r cos theta square root x square plus y square equals to r. So our new bounds for this upper semicircle are r from 0 to 2 and theta from 0 to pi. So next step is the first we integrate the r first, so the answer we will get is 2 cos theta. After that we even integrate again using that answer 2 cos theta. So after we integrate, we got 2 sin pi minus 2 sin 0, so the final answer will be is 0. So next is the surface area of a paraboloid. For the problem 2, we are finding the surface area of the paraboloid z equals to x square plus y square that lies below the plane z equals to 1. So we are starting from the standard surface area formula as given. So after that, taking the partial derivatives of z x square plus y square, and after that we get 2x and 2y, and after that we substituting these into our radical simplifies the integrand to this. So next is the polar conversion. Since the region is circular, we project the intersection onto the xy plane by setting x equals to 1. So it will giving us the boundary unit circle x square plus y square equals to 1. So after that we converting to the polar coordinate. So this is the basic polar coordinate x square plus y square equals to r square. And after that the area element dA equals r dr d theta. So after that we can set up our new double integral. As you can see, since the integrand doesn't depend on theta, integrating d theta from 0 to 2 pi simply factors out as 2 pi. So after that we need to integrate to solve the remaining single integral. So we use u substitution. So as you can see, u equals to r plus 4r square. So du will be 8r. So the lower bound changes from r equals to 0 and u equals to 1. So the upper bound changes from r equals to 1 to u equals to 5. Substituting these in gives. So as you can see, this is the step for the integration. So simplifies the coefficient gives pi over 6. So after that, our upper and lower limits, we get our exact surface area. So as you can see, 5 3 over 2 minus 1 over 6 pi. Thank you. Okay, for the next question is the question 3a1. So first, this is the question for the triple integral in Cartesian coordinate. So we need to solve step by step x, y, z. So first one is to integrate the xy respect to the x. After that, we need to solve the integral y. So the answer will to 1 over 8 bracket 16 minus 8 z square plus z power 4. So after for the finally is we need to integrate with respect to z from 0 to 1. So this is the final answer for the question 3a1. So the answer will be 203 over 120. So next is the question 2, double integral over a rectangle. For part 2, we find the volume under the surface 8 minus x square minus y square over a rectangular region where x equals negative 1 1 and y 0 to 2. So this is the question for the part 2a. So first one we need to solve the y first, integrating with respect to y gives. So this is the first integral, 40 over 3 minus 2x squared. So after that we need to integrate the x. As you can see, we after we integrate, we need to replace the 1 and negative 1 to the equation. So the final answer for this question 3a is 76 over 3. So for the next question is 3b, spherical coordinates. We convert a complex Cartesian integral into a spherical coordinate. The boundaries describe a solid bounded above by the sphere x square plus y square plus x square equals to 32. So this is our new spherical limits. This is the three spherical limits. So next, we need to integrand 3x square plus 3y square plus 3z square becomes 3p square, and the volume elements become as given in the manual calculation. It splits into three independent different integral, as you can see for the this question. So as we can see, we need to split into three independent single integral, as you can see in the manual calculation. So after that, we need to evaluate for the each part. So first one is 2 pi for the theta integral. After that, we can get the answers from the 4 and 5. So after that, we multiply everything together. So we will give the answers to 24,576. Y equals to square root 2 minus 1 over 5. So next is the question 3, C1 and C2. So first we are going to look at the C1. So the first is polar integral in the first octant. For question 3, C1, we integrate x square plus y square over a region between the circles of radius 1 and 2 in the first octant. So we switching the polar coordinates, x square plus y square equals to r square, and dA equals dr over d theta, making the integral r cube. In the first octant, theta goes from 0 to pi over 2, and r goes from 1 to 2. So this is the manual calculation to get the final answer. So for the final answer is 15 pi over 8. So finally, for the C2, we find the area enclosed between y equals sin x and y equals cos x from x equals pi over 4 to x equals pi over 2. In this interval, sin x is above cos x. As you can see, this is the manual calculation for the C2 and how to solve it. So after we integrating, gives minus cos x minus sin x. So this is the limits for the after we integrate. So we just replace it with the x. So the result will be negative 1 minus bracket negative square root 2. We can simplify it, so it will become negative 1 plus square root 2. So that's all from me. Thank you.
Now I will present the MATLAB stimulation part for question 1. For question 1, the manual correction answer is 0. So the purpose of the MATLAB stimulation is to verify the manual answer and also show the region of the integration. First, we identify the region from the given limits. The region is upper half of the circle with the radius 2. Because of that, the polar coordinates are suitable for this question. In MATLAB code, first I will define the variables. I use the symbolic variables r and theta, so the MATLAB can do the exact integration. The important calculation line is this one. This line means a MATLAB integrate the function first with respect to r from 0 to 2, then with respect to theta from 0 to pi. After running the code, the MATLAB gives answer 0. This matches the manual calculation so that manual solution is verified. The graph generated by MATLAB shows the upper semicircle region. This confirms that the polar limits used in simulation are correct. Now I will present the MATLAB simulation for question 2. For question 2, we need to find the surface area of the parabola below the plane z equals to 1. The manual calculation gives the final answer as a pi over 6 with the bracket 5 power of 3 over 2 minus 1. So the purpose of the MATLAB solution is to verify this answer and show the 3D surface. First, we identify the boundary. Since the parabola is below the plane z equals to 1, we substitute z equals to 1 into the equation. This gives a region is a circle with a radius 1. In MATLAB, I use the symbolic variables r and theta because the region is circular and polar coordinates are easier. This calculation line is important. The line means the MATLAB integrates the surface area formula in polar form. The r at the ends from dA equals r dr d theta. The limit for r is from 0 to 1 and the limit for theta from 0 to 2 pi because the region is a full circle. After running the code, the MATLAB gives the exact answer with in the decimal 5.330435, same as manual calculation. So the MATLAB result matches the manual calculation. The graph generated by the MATLAB shows the paraboloid and the plane below z equals to 1. This helps us to confirm the surface area is already taken below the plane. Now I present the MATLAB simulation for question 3a Roman 1. The question is a triple integral. The manual calculation gives a final answer as 203 or 120. So the purpose of this MATLAB simulation to verify the manual answer using a symbolic integration. In this question, the limits are already given in Cartesian form, so we do not need to convert into polar or spherical coordinates. We just follow the same order as the given integral. In MATLAB, I define x, y, z as a symbolic variables. This allows MATLAB to perform the exact integration. And this is the calculation line. The line means the MATLAB first integrate with respect to x from 0 to y, then integrate the respect y from 0 to square root of 4 minus z square. Lastly, integrate the with respect to z from 0 to 1. After running the code, the MATLAB gives the exact answer 1.69166667. This is the same as a manual calculation, so the answer is verified. The graph generated by MATLAB shows the 3D region based on the given limits. They help us to visualize the solid region used in triple integral. Now I will present the MATLAB simulation part for question 3a Roman 2. We are given a double integral over rectangular region. The function is 8 minus x square minus y square and the region is from x equals to negative 1 to x equals to 1 and from y equals to 0 to y equals to 2. The manual calculation gives a final answer 76 over 3. So the purpose of the MATLAB simulation to verify this manual answer. In MATLAB, I define x and y as a symbolic variable. Since the limits are already given in Cartesian form, we did not need to convert to polar coordinates. The important calculation line is this one. The line means the MATLAB first integrated with respect to y from 0 to 2, then MATLAB integrated with respect to x from negative 1 to 1. After running the code, the MATLAB gives the answer in a decimal form, which is 25.333. This matches the manual calculation, which is in fraction form 76 over 3. So the answer is verified. The graph shows the rectangular region used in double integral. They confirm the integration limits are correct. Now I'll present the MATLAB simulation part for question 3b. We are given a triple integral. The question is more suitable to solve using a spherical coordinate because the region is bounded by sphere and cone. For the question, the upper boundary represents the sphere, um, x square plus y square plus z square equals 32. Therefore, in spherical coordinates, the radius limit is rho equals 4 root 2. The lower boundary is the cone equals square root of x square plus y square. This gives the angle limit p equals to pi over 4. In MATLAB, I define rho, p, and theta as a symbolic variables. The original integrand is a 3x square plus 3y square plus 3z square. In spherical coordinates, this become a 3 rho square. Since the volume element in spherical coordinates is rho square sin pi, the full integrand used in MATLAB becomes 3 rho power 4 sin pi. And the important calculation line is the highlighted line in the comment. This means the MATLAB first integrated with respect to rho from 0 to 4 root 2, then it's integrated with respect to p from 0 to pi over 4. Finally, it integrated with respect to theta from 0 to 2 pi. After running the code, the method gives an answer 24567 pi over 5 times bracket root 2 minus 1. This matches the correct manual evaluation, so this answer is verified. The graph generated by MATLAB shows the region inside the sphere and above the cone. This confirms the spherical coordinates are suitable for this question. Now I will present the MATLAB simulation part for question C1, question 3C1. We need to evaluate the double integral of x squared plus y squared over the region between two circles. The region between the circle x squared plus y squared equals to 1 and the circle x squared plus y squared equals to 4 in the first quadrant. Since the region is circular, polar coordinates are suitable. In polar coordinates, x squared plus y squared becomes r squared. Also, the area element dA becomes r dr d theta. After the conversion, the integrand becomes r power 3. In MATLAB, I defined r and theta as a symbolic variables. This important calculation line, as you can see in the highlighted in the slide. This line means MATLAB first integrate with respect to r from 1 to 2. Then it's integrated respected to 0, integrate with respect to theta from 0 to pi over 2. After running the code, the MATLAB gives answer 15 pi over 4, over 8. That matches the manual calculation, which is same also. So the matches, so the answer is verified. The graph generated by MATLAB shows the region between the two circles in the first quadrant. This confirms that polar limits used in simulation are correct. Now I will present the MATLAB simulation for question 3C Roman 2. We need to find the area of a region enclosed by the curve y equals to sin x and y equals to cos sin x and x equals to pi over 4 and x equals to pi over 2. In this interval from pi over 4 to pi over 2, the curve sin x is above the curve cosine x. So the area is founded by integrating sin x minus cosine x. In MATLAB, I define x as a symbolic variable. This is the important line in the code which I highlight in the slide. This line means MATLAB integrates sin x minus cosine x with respect to x from pi over 4 to pi over 2. After the running the code, MATLAB gives answer root 2 minus 1.
This matches the manual calculation also, so the answer is verify. The graph generated by the MATLAB shows the shaded area between the sine curve and cosine curve. This means the upper curve is sin x, the lower curve is cosine x in the given interval.
Now, in conclusion, multivariable calculus provides an effective method for solving problems involving multiple variables and constraints. Mathematical modeling and optimization techniques help determine the most efficient and practical solution. Partial derivatives and related calculus concepts enable accurate analysis of complex systems and functions. The results demonstrates the practical application of multivariable calculus in engineering and real-world scenarios. Overall, the project enhances understanding of multivariable calculus and its importance in problem solving and decision making. Next up, we have a few meetings that we did do online, and these are a couple examples that we did take a screenshot of doing the simulation, the calculation, and the briefing of the project. That is all from us, Group 5. Thank you so much for your attention.